Hi everyone, my name is Haochen Huang. Today I'm glad to present our work on PYLIVE, on-the-fly code change for Python-based online services. This is joint work with my collaborators from USENIX. Today, more and more important backend services with high availability requirements are written in languages like Python. Many companies use Python to build their main online platforms. For example, YouTube front-end server is built using Python. So do Instagram and Quora's main web services. There are also various open source services in Python, such as Web Framework and e-commerce. These online services have high requirements on availability. A recent survey shows that 4 nines of uptime has become the minimum availability standard for most services. This news also shows that 1 hour server downtime can cost millions of dollars. However, high availability becomes challenging when there are code changes to apply to systems, and these code changes are necessary. First, engineers need on-the-fly logging when their online services exhibit some abnormal behaviors. Production run information is useful for diagnosing challenging issues that are hard to produce in testing environments. Also, on-the-fly profiling can be very helpful for diagnosing production run performance issues. However, the profiling overhead is a big concern. We want to build a tool to let engineers dynamically profile a small set of specified functions for a short period of time with affordable overhead. Third, we want to build a tool to let engineers dynamically apply urgent patches to fix some critical bugs or security issues without stop and restarting the servers. Motivated by Python's popularity and the demand of applying code changes while keeping high availability, in this paper, we design and implement a framework called PYLIVE that enables dynamically changing Python programs for on-the-fly logging, profiling, and bug fixing on production systems without restarting them. One common practice for code updates that avoids the whole system downtime is rollout deployment. It involves a cluster of services, and these servers are restarted batches by batches. However, rollout is not the best choice for dynamic logging and profiling for 2 reasons. First, rollout updates still require restarting each server, so it will lose the memory states across updates. Second, a rollout deployment is heavyweight and an overkill for just collecting logging or profiling information. Sometimes, only a few servers of a fleet exhibit abnormal behaviors. If engineers want to diagnose the issue, a simple logging patch needs to be batched together with many other patches and will wait a long time until deployment. PYLIVE provides a better solution. First, it requires no restart of services instance, so it retains the issue states. In addition, it enables dynamically adding logging or profiling statements to a running program quickly, and also removes the statements flexibly. So PYLIVE complements rollout deployment. PYLIVE realizes portable and dynamic code change by leveraging Python's language features. It relies only on the interfaces provided by standard Python interpreters. First language feature is meta-object protocol. It provides an interface to dynamically modify the metadata, including function body, function interface, and class attributes. The figure shows how to change an existing function's code body and class attributes at runtime. Second feature is dynamic typing, which allows changing variable types during runtime. This is because Python defines and checks variable types at runtime. For example, a variable A can be changed from a string to an int. Now, let's take a look at PYLIVE's interface. The instrument interface can instrument logging or profiling code to specified locations in certain functions or modules. It is useful to diagnose bugs or performance issues. The interface is at the right side with scope, join point callback, and time. Let's take a look at a real-world issue from the Oscar e-commerce system. This is a critical performance issue, preventing customers from buying products. Now, engineers want to use PYLIVE to instrument code to profile the system. Scope is a list of function or module names that need to be instrumented. Here, engineers define the scope as the methods in two suspicious classes. Joint point callback is a key value dictionary of instrument location and callback code to instrument. PYLIVE supports flexible joint points at different granularity, such as function begin or end, or before or after a line. Finally, time allows engineers to specify when to perform an instrumentation and when to revert it. They may want to profile only when the system is lightly loaded for a short time. Next, we have the redefine interface. It is for code changes that replace the definitions of existing functions and data structures with new ones. To perform such changes, engineers use the following interface. preffunc is a user-defined Python function that engineers need to provide, and it is executed before making the change. Old-new map is a key-value dictionary that specifies the change. Each pair specifies an old function need to be replaced by a new function. To add a field to a class, you can also specify the field name and its initialization code, like the second line. Finally, save point defines at which execution point is it safe to apply the specified change. We will introduce it later. PYLIVE faces three major challenges: how to support dynamic changes for function interface, function body, and data structure, how to identify safe change points to apply a change without causing inconsistency problems, how to update programs with multiple threads and multiple processes. We'll go through the first two. Challenge 1, support dynamic changes. PYLIVE supports changes on both function interface and code bodies. Changing function interface includes altering the number of parameters, parameter types, and function names. To make these changes, we utilize Python's meta-object protocol and dynamic typing. For example, for parameter number changes, PYLIVE directly modifies the function's parameter list. For function body changes, PYLIVE supports both redefine and instrument. For both types, PYLIVE replaces function's code object as a whole. For instrument changes, PYLIVE also relies on bytecode rewriting. Another question is how to deal with the caller functions when callee is changed. For changes that only modify callee function bodies, PYLIVE needs not to change the callers. This is because Python function calls are made by function names instead of addresses. Every time a function call happens, Python interpreters translate its name into address by looking up its metadata. Data structure changes include changes to class attributes, object attributes, and methods. PYLIVE also relies on meta-object protocol to change the metadata. Note that object attributes are more difficult to change since they are individually stored in a different object. PYLIVE utilizes Python's garbage collector to check live objects and modify each one individually when a change is requested. The second challenge is to identify the safe change point. Changing code at runtime is not always safe. For instance, changing a function when it is executing may cause inconsistency problems. Therefore, dynamic code change systems need to carefully choose a safe execution point to apply a change. Note that choosing the safe update point is only necessary when applying patches. PYLIVE can always apply code changes for logging and profiling, as they only add code but do not change the existing code. PYLIVE supports two kinds of save points and let engineers select one. First, quiescence of the change functions. This requirement means a change is only applied when the change functions are not under execution. To be specific, PYLIVE checks every thread stack for any change function. If any change function is on a stack, defers the change. However, function quiescence may not be enough for safety when the change function modifies shared states. Consider the example here. Two functions lock and unlock need to be changed, and both of them modify the lock state. Applying the change when the program is executing between the calls to lock and unlock is not safe. The new unlock may be called with an old lock state and the behavior is undefined. To address this, PYLIVE allows engineers to provide a customized Boolean function to decide when it is safe to apply a change. This figure shows an example of state check function. It checks if no lock is held before applying the change. PYLIVE evaluates the function and only applies the change when it returns true. Now we go to the evaluation part. We evaluate PYLIVE with 20 real-world cases from 7 Python-based applications, as shown in this table. It covers widely used production web framework and server and many e-commerce services. These services need to be almost non-stop, since any downtime can result in revenue loss. We measure the performance benefit of PYLIVE to apply code changes. We use throughput as a performance metric and normalize it. We compare it with the typical restart approach. Modify code offline, stop the services, and restart the service immediately. For profiling, we also compare PYLIVE with cProfile, which is Python's official profiling tool for collecting comprehensive profiling in testing environments. For logging cases, PYLIVE's benefit mainly comes from avoiding the time to restart and warm up. In this figure, the x-axis is the timestamp and the y-axis is the normalized throughput. We can see that the throughput drops to 0 for the red line, which means restart. On the other hand, PYLIVE can avoid 3 seconds downtime caused by the restart. PYLIVE also avoids 2.3 minutes warm-up time. And PYLIVE imposes only 0.1% overhead during normal executions. For profiling cases, PYLIVE makes the performance impact affordable in production run systems. Its benefits come from 2 aspects. First, enabling cProfile needs an application restart, causing downtime and warm-up time. The figure shows PYLIVE can avoid the 3 seconds downtime and 4.5 minutes warm-up time. Second benefit is that PYLIVE allows engineers to perform customized profiling. cProfile still imposes 35% performance downgrade after warm-up because it profiles every function. PYLIVE can be customized to only profile the relevant functions suspected by engineers and thus reduce the profiling overhead to only 1.4%. To summarize, we propose a framework called PYLIVE that leverages Python's language features to support dynamic code change for on-the-fly logging, profiling, and patching in production run systems without restarting. It only relies on standard Python interpreter and can be easily adopted. Comparing to restart, PYLIVE avoids service downtime and warm-up. For profiling, PYLIVE adds affordable overhead. We evaluate PYLIVE with 7 widely deployed Python-based systems for online services. It works for 20 existing real-world cases with dynamic logging, profiling, and patching. PYLIVE also helped 2 systems diagnose 2 new performance issues. That's all. Thank you.